This video provides an introduction to graphing polynomial functions. Polynomial functions are considered simple functions. They're really nice to work with. Graphs of polynomial functions are both continuous and smooth. A function is continuous if there are no holes or jumps that occur and the graph can be drawn without picking up your pencil. A function is smooth if there are no sharp corners. The graphs of all polynomial functions have both these characteristics, and when they're graphed, they kind of have like a wave look to them. There are a few more vocab words we need to discuss before we talk more about graphing. If f of x is a polynomial function and a is a real number, then x equals a is a solution or root to the equation f of x equals 0. We're used to the vocab word solution. It's the answer when we solve an equation, but the term root can be used as well. Solution and root are interchangeable words. X equals a is a 0 of the function f of x. So a 0 is simply the solution when you set the equation equal to 0 and solve. X minus a is a factor of f of x. So if we have x equals a to be a 0, to get the corresponding factor, we just set it equal to 0. So we would get x minus a equal to 0, and that x minus a is the factor. That's what our third bullet says. And then lastly, a comma 0 is an x-intercept of the graph f of x. So if you take your 0, which is the solution when you set it equal to 0, aka letting y be equal to 0, if you rewrite that as the ordered pair a comma 0, then you have an x-intercept. Let's find the zeros of the following polynomial functions. First up is f of x equals x to the third minus 7x squared plus 12x. To find the 0, we're going to set it equal to 0 and solve. Notice that we have a common factor of x on the right, so we'll factor that out. And then we can factor that quadratic further, x minus 4 times x minus 3. Now that we're fully factored, we can set each one of our factors equal to 0 and solve. This polynomial function has 3 zeros. X equals 0, x equals 4, and x equals 3. Let's take a look at our next example. G of x equals x times x minus 2 cubed times x plus 1/2 squared. Notice that this polynomial function is in factored form. I'm going to write it in expanded form. It's going to be x, and we're going to have 3 factors of x minus 2 and 2 factors of x plus 1/2. To identify the zeros, we're going to set this equation equal to 0. We want to get our polynomial in factored form, so we can set each factor equal to 0 and solve. Notice that it's already in factored form. Each one of our factors is going to give us a 0. So our first factor of x gives us a 0 of 0. These next three factors, each one of them is going to give us a 0 of 2. And our last two factors, each one of those factors is going to give us a 0 of negative 1/2. We only have three unique zeros, 0, 2, and negative 1/2, but notice that our 0 of 2 actually showed up 3 times because we had 3 factors of x minus 2, and our 0 of negative 1/2 showed up 2 times because we have 2 factors of x plus 1/2. These zeros are said to have multiplicity because they showed up multiple times. So here's our definition of multiplicity. If x minus a raised to the n is a factor of a polynomial f, then a is called a 0 of multiplicity n of f. So going back to this previous example, we would say that 0 had multiplicity 1 because it showed up just one time. Our 0 of 2 has multiplicity of 3 because that factor showed up 3 times. And negative 1/2 has multiplicity of 2 because it showed up 2 times. We don't actually have to write it in this expanded form to get the multiplicity. We can just look at the exponent on those factors. We care about the multiplicity of our zeros because the multiplicity of the 0 tells us what the graph does at the corresponding x-intercept. Remember that zeros and x-intercepts are pretty much the same thing. An x-intercept is just written as an ordered pair. So the graph can either cross the x-axis or just touch the x-axis at the corresponding x-intercepts. The multiplicity of the 0 tells us which is going to happen. Zeros with even multiplicity correspond to x-intercepts where the function just touches the x-axis but doesn't cross it. Zeros with odd multiplicity correspond to x-intercepts where the function crosses the x-axis. You'll see I have the additional word kisses in here. I like to use the word kiss instead of touch because kiss has 4 letters in it, which is an even number of letters. So I remember that even multiplicity goes with the word that has an even number of letters. And then if we use the word cross, cross has 5 letters. 5 is an odd number. So this reminds myself that for odd, I want to use the word with an odd number of letters, which would be cross. So even multiplicity, we're just kissing the x-axis. Odd multiplicity, our graph is actually going to cross the x-axis. Now, with the odd ones, we can even be more specific. Because if you look at this graph, 2 different spots it crosses, but notice that the way it crosses looks different. At negative 2, it kind of does a wiggle when it crosses, and at x equals 0, it's just a straight cross. If the multiplicity is 1, the graph goes through the x-axis straight. And if the multiplicity is a higher odd number, the graph wiggles through the x-axis like it did at x equals negative 2. I remember this because a line, y equals mx plus b, is degree 1. So when the 0 has a degree of 1 on it, it's going to behave like a line, which just goes straight. But any other odd number higher than 1, it's going to wiggle through just like the graph of x cubed. Remember, it has this kind of shape to it. It does a wiggle in the middle. Another piece of information to help us when graphing is the end behavior of the graph. Since polynomial functions are simple functions, they all behave relatively similarly. So let's think about the most basic even-degreed polynomial that you know. That would be y equals x squared. Think about the shape of that. When x squared has a positive leading coefficient, we have a parabola that points up. And when x squared has a negative leading coefficient, the graph is a parabola pointing down. All even-degreed polynomials have similar end behavior to x squared. So any even-degreed polynomial, x squared, x to the fourth, x to the sixth, x to the 100, when it has a leading coefficient that is positive, is going to have end behavior of entering through the top and exiting through the top. Now, what happens in the middle can be different, and we'll learn more about that in the next video. Any even-degreed polynomial with a negative leading coefficient will have the end behavior of entering through the bottom and then exiting out through the bottom as well. Now let's talk about odd-degreed polynomials. The most basic odd-degreed polynomial we know is y equals x. When the leading coefficient of a line is positive, that means that the slope is positive and the graph is going to point up from left to right. Comes in from the bottom, out the top. Any line with a negative leading coefficient, which would be a negative slope, points down from left to right. Notice that it enters from the top and exits out the bottom. All odd-degreed polynomials have the same end behavior. So any odd-degree polynomial with a positive leading coefficient is going to enter from the bottom, do some stuff in the middle, and then exit out the top. Any odd-degreed polynomial with a negative leading coefficient is going to enter from the top, do some stuff in the middle, and then exit out the bottom.